All right, how's it going, everybody? So today we're going to go ahead and jump into chapter number 9. Just the homework problem for that. We've got number 4, number 6, number 11, number 14, 19, 21, 28, 38, 42, and 51. So starting off with number 4, there's actually 3 portions of it. Basically doing the same thing over and over again. Only difference is that they give you a different material and of course different size of material and all that stuff. But what they want you to do is to calculate the stress developed in the members that are each subjected to an axial tensile load of 70 kilonewtons. The first one that they want you to deal with is a steel bar that is 25 millimeters by 50 millimeters. And in order for us to do that, we need to first calculate the area. So this is going to be number 4 here. And one thing we do know is the axial tensile load is 70 kilonewtons. So actually I just want to kind of pop this in over here just so I have it available to me. We've got 70 kilonewtons, which as we all know, 70 kilonewtons is just really 70,000 newtons, or 70 10 to the third newtons. However you want to write it, just make sure that you are aware that it's not just 70, because I see that happen quite often. Actually, students just put 70 in for their load, not realizing that it's actually 70,000. So first one's going to be the area of our steel member. I believe it said it's a bar, so that bar is going to be square in shape. So the cross-sectional area is going to be just 25 times 50, and we get 1250 millimeters squared. So therefore the stress developed in this one is just going to be, and our equation is going to be always the same, P over A, load over area. So we got our 70 10 to the third divided by our 1250, and that's going to give us 56 megapascals. Remember to make sure you convert your units when you are doing these. It won't just be, I guess you can just kind of leave it as is originally, but you can always just convert it to megapascals, make life a little bit easier for you. So that was, we're going to write A up here. Next up we're going to do is B. The area for that is going to be the 0.7854, the pi over 4 times d squared, because they're saying that this is a 150 millimeter diameter wood post. And so the area for that is going to be the 0.7854 times 150 to the second power. And after we calculate that up, we get 17.68 times 10 to the negative third meters square in this case. So therefore our stress developed in this member here, and again this is axial tensile stress as well. We're going to say that this is the same load, 70. Divide that by that area that we just grabbed, which is the 17.68. And we get 3.96. Yeah, 3.96 times 10 to the 6 pascals. So I'm going to just round that up, 3.96 megapascals. And then lastly, for part C, they want us to do a 25 millimeter diameter steel tie rod. So again, this is going to be a diameter, so we know the area equation that we need to use is the 0.7854 is 25 squared, and this one we get 490.9 millimeters squared. So therefore the stress developed, tensile stress developed, is again our 70 kilonewtons there. Divide that by our area that we grabbed, and we get a total value of 142.6 megapascals. All right, number 6. Number 6 states to determine the stress in the two segments of the bar that is shown. Segment A has a diameter of 1¼ inches and segment B has a cross-sectional 2" by 2". So we have, I'm just kind of draw what we have here. We have something that looks like that, and then we got a little bit bigger here. That might not be the right length, but whatever. We got some dimensions on here. This is 1 1/4, I believe it said. And this has a cross section of 2" by 2", which I guess I can't really draw it, but I'll just put 2 here. And we got our forces. Draw these in red. This is going this way, it's 22 kips. Going this way, it's 12 kips. And coming this way, it's 10. So guys, just remember also when you are doing problems like this, they have to be in equilibrium. So that's why we have 10 coming in on the left. Then we got 12 also coming in on the left. 10 plus 12 equals 22. And then we got 22 coming in on the right on that side. So don't let it scare you if you see some of these are kind of broken up in that manner. So number 6, we've got a load. We got a load here. I'm gonna do segment A side first. Let me just plug that in here. A is gonna be, we have a load of 10 kips coming in at location A. The area, and we'll just call this P, right? Area is gonna be the 0.7854 times 1.25 squared. So that's gonna equal 1.23. So therefore, our stress in this case is going to be equal to that force over area, 1.23, which gives us an 8.13 kips per square inch value. And then for segment B, and I'll just write in here, this is segment A, this is segment B. Then for segment B, we've got a force coming in at 22, and then the area of this one is actually going to be 2 times 2. It's got a cross-section area of 2 and 2 there, which gives us 4 inches squared. And so therefore the stress on this one is going to be 22 divided by 4, which gives us 5.5 kips per square inch. Next, we have number 11. Number 11 states to compute the force required to punch a 1" diameter hole through a 1½ inch thick boiler plate. The ultimate shear strength for the material is 42,000. All right, so in this case, let's see, the force required to punch. So what we're looking for is the force, which is P. And we know in this case that the shear strength, right? We already have the shear strength, so I'm gonna just kind of pop out over here. We already have the shear strength, which is tau. Tau is still equal to P over A. So therefore we can just say that P is just equal to tau times A. So therefore, all we really need, because we have tau, so P is equal to tau, which is 42,000 psi. That's psi times A. We don't know A yet, but we can easily solve for that. A for this object here is going to be pi. Oops, I shouldn't draw it like that. Pi dt, diameter and the thickness. So we've got 3.14, and this value might change a little bit. It just depend on if you use 3.14 or 3.14, whatever, or if you just punch in the pi symbol in your calculator. But 3.14, the diameter was the 1, the thickness of the boilerplate was 0.5. So therefore we get a value of 1.571 inches squared. So I can just plug that in here. 1.571, which gives us 65,980 pounds. Next, we have number 14, and number 14 says, let me just write this first. 14, where's 14 at? So given lambda equals 1.2 inches and L equals 100 feet, calculate epsilon. Then B, okay, I see what they're doing. So they're giving us a couple of values and they want us to calculate the remaining. This will be fairly simple, straightforward, because it's all just calculations here at this point. Whoops. All right, so they want us to calculate in A. They want us to calculate epsilon, which equals lambda over L. In B, they want us to calculate L, which is lambda over epsilon. And then lastly, C, they want us to calculate for that, which is lambda over, or not over, epsilon times L. A, they give us the values of 1.2 and 100. So we'll do 1.2 here, and this will do 100, which always remember, everything needs to be in the correct units. So my lambda was given to me in inches. My length is here, it's given it to us in feet, so we need to convert that over to inches. So we just multiply by 12. I guess I can write inches per foot here. And then we get a total value of 0.001 inch per inch. Down here we have 0.5. Again, make this times 12 divided by our epsilon, which they gave us 0.00030, and that's going to equal just 20,000 inches. Or if you want to divide that up, we get 1667 feet. And then lastly here, they give us L as 1,000, epsilon is 4.2 times 10 to the negative 4, or whatever it is. And we get Oops. Wrong problem right in here. Alright, yeah, so epsilon 0.00042 times the 1,000, and that gives us 0.42 inches. That was 14, so number 19. 19 is an aluminum rod 25 millimeters in diameter and 4 meters long is subjected to an axial tensile load of 65 kilonewtons. They want us to compute the stress, strain, and the total elongation. So we'll just go ahead and write this down here. So it's an aluminum rod, so we know it's a rod, so it's gonna look something like that, right? This aluminum rod is 25 millimeters in diameter and 4 meters long. And it has axial tensile load of 65 kilonewtons here. And it said it's tensile, so tensile, tension, going this direction, 65 kN. So now we can actually solve for this problem here. The first thing that they want us to solve was the stress, then we saw the strain, then we solved the total elongation. So the stress equals P over A. P, 65 kilonewtons, remember that's 65,000. A is going to be the 0.7854 times D squared. And so therefore we get 132.4. Strain, epsilon, using our S over E, which I'm not even going to call that S for stress. I'm going to just go ahead and use the Greek symbol, get more familiar with that there. We get 132.4. And this E is a standard value. You can find that in the back of the book. .89 times 10 to the third. And then C we get 1.89 times 10 to the third value there, times the total length, which is the 4 meters. And this, we'll probably have to convert this over into our, yeah, we're gonna have to convert this so that it's in millimeters. So let's just do that. And so therefore the total is 7.56 millimeters. Twenty-one is a titanium alloy bar, and this titanium alloy bar elongates 0.5 inches when it is subjected to an axial tensile load of 100 kips. So let me see if I can draw that here real quick. Titanium alloy bar. Actually, let me move this down. Axial tensile load, so it's in tension. What did it say, 100 kips? Yeah, 100. bar is 16 feet long. So we might need to convert that to inches. Just take note of that. Has a cross-sectional area of 2.25. So it looks like they give us the area. Cross-sectional area equals 2.25 inches. Compute the modulus of elasticity. Use a proportional limit of 125 KSI. So the prop limb, 125 KSI, and the E is what we want to solve for. One other thing they did give us is the elongation, which is 0.5. So I'll write that up here also. Elongation is 0.5. Just so we are aware of it, we have it. Yeah, so in order to solve this problem, first need to solve for that stress there, P over A, which is going to equal to 100 for P, divided by 2.25. They give us that directly, and we get 44.4 KSI. As the prop limb is 125 KSI, this here is below prop limb, so it's okay. And then after we grab that, we can now solve for our modulus here, which is PL over A lambda, which we know P over A is what? Just our stress there. So we can just take that, L lambda, which gives us 44.4 times L, which is the 16 feet. Oh wait, nope, not 16 feet. 16 times 12, which gives us, this is L, 16 times 12. 192 inches. So this is times 192. And we're going to divide that by lambda, which they gave us, the elongation, 0.5, for a total of 17,050 KSI. That was 21. 28. Number 28. 28. Number 28 stays. Got to change the page. Where is that at? Oh, a column is supported by a base plate, pedestal, and footing as shown. The load applied on the column is 60 kips. Neglecting their weights, find the bearing stress under each of the 4 elements. So yeah, so this problem here, don't really need to draw this problem out, but I guess I can kind of sort of draw it. So we've got a base here, then we've got another base sitting on top of that, then we got a skinny base on top of that, and we got like a tall there, and then we've got 60 kips here. W12 by 40, 14 by 14, 24 diameter. I'm gonna just put the diameter symbol here. And this is 4 foot by 4 foot. All right, and we got to find a bearing stress. Bearing stress under each of the 4 elements. So for this one, and I'm gonna just call these out as what's it called? Kind of their name, not the whole name though. C is gonna be for the column. This is gonna be B for base plate. This is gonna be P for pedestal, and square footing is just gonna be F for footing. So that way we know what we're talking about here. So when I do C, that's just going to be our 60. Oops. C is not equal to that. We're just saying that this is C. C is equal to our stress, or stress is equal to 60 over, in this case, 11.7 for the W12 by 40. Got 11.7 here, and the total value is 5.13 KSI. Next is the base plate. So B, it kind of looks backwards, but it's all good. B is 60 again. Divide that by our area here, which is 196. And so therefore we get 0.306 KSI. P is the next one. Again, 60 for our force. Divide that by our area. Area in this case is 452.4. Remember, this is a diameter, so we got to use a diameter equation for that. 0.133 KSI. And then lastly is F for footing. And we get 60 over 16, which is equal to 3.75 KSF. And recall or take note that I'm calling this KSF, which is kips per square foot rather than kips per square inch. The only time this is okay is if you're not actually having anything else that's in inches for you to use in calculations, or else it'll mess you up. Since this is the only calculation we're doing, we can leave it in feet, but generally we would take this 4 times 4 and then turn into what's 4 times 12? 48. So 48 times 48, and then use a different value for that and get KSI. But we're okay with this one. 38. Number 38 now. And 38 says to calculate the force a punch press must exert if it is to punch out a large washer from a strip of 5mm thick sheet steel with an ultimate shear strength of 400 megapascals. The washer dimensions are as follows. The hole is 27mm and the outside diameter is 64. So I think about this as being like a hollow shape. A hollow shaped object or whatnot, so your equation will have to factor that in, which essentially is our ID. They said was the 27 millimeters. Our OD, inner diameter, outer diameter, that's what ID and OD stand for. Inner diameter, outer diameter. OD is 64 millimeters, and they did give us the actual thickness of this, which was 5mm. So THK 5mm, and they also give us the ultimate shear strength. 400 megapascals. And I think that's it. I think that's all they give us. Yeah, now we just got to calculate the amount of force it would take to punch out a hole this size. So for number 38, as we know, we have our ultimate shear strength, which is equal to what? P over A. So in order to find P, we just have to rearrange our equation a little bit. And remember, this is the ultimate shear strength, ultimate times A, which is going to be 400 times whatever A comes out to be. A is equal to pi dt, but in this case it's going to be pi t. I usually put like d1 d2, but I'm gonna just, since I called it id and od up here, I'm gonna just say id minus od. Well, not minus, sorry, id plus od. And so therefore we get 3.14 times t, which was what, 5, times 27 plus 64, which gives us 1.429 times 10 to the third millimeter squared. So then we can plug that back into here, 1.429 times 10 to the third, which gives us 572 kilonewtons. And I just put a box around this and call it the answer just because I have different equations below it. So if anyone was looking at this, I want them to know that this is my answer versus having to look all the way down at the bottom and get lost from there. 42, and the last one is 51. 42, we have a 25 millimeter diameter aluminum rod, 3 meters long, is subjected to an axial tensile load of 67 kilonewtons. Assume that a proportional limit is 207 megapascals. Compute the stress, strain, and the total elongation. So, prop limb. (207 megapascals). Axial tensile load, P, 67 kN. Diameter, 25 mm. And L for length is 3 m. So these are known values. Our unknown values is stress, strain, and total elongation. So stress, strain, what's strain? E or epsilon. Total elongation is lambda. And so therefore we have, well, first thing that we know we also need is our area for our stress. Area is going to be 491 millimeters squared. I'm also just going to write this up here just so we're all on the same page. Again, make sure you're taking note that this is 67,000 newtons, not just 67 newtons. All right, so stress. This is tensile stress, right? Tensile stress is equal to our P over A. P over A is going to be 67 10 to the third divided by A, which was the 491, which equals 136.5 megapascals. this here is less than prop lim I'll just put will survive. It's less than the proportional limit there. So we can continue on further. Epsilon is going to be (136.5) divided by E, which we can grab E from the back of the book, 70 10 to the third, which gives us 1.95 10 to the negative third. Did I put negative on the other one? I think this is supposed to be negative as well. I gotta double check my calculations. I think I accidentally wrote positive, or yeah, double check that. Yeah, this may have to be negative. I just randomly thought about that. And if not, then this might be positive also. I have to check and see there. But yeah, so that's 1.95 times 10 to the negative third. I believe they're supposed to both be negative there. Because 70,000 is way larger than 136. Do I have my calculator with me? Let me see. Yeah, this would be 1.95 times 10 to the negative third. Yeah. Sorry about that. Lambda equals epsilon L 1.95 times 10 negative third. L, which is 3 meters, which in this case, this is in meters. We need it in millimeters because everything else is in millimeters, so we got to convert it. 1,000. And therefore we get 5.85 millimeters. Cool. And then lastly, we have number 51 here. Number 51 is going to be, for the truss shown, compute the total deformation of member CD due to the applied load of 100 kips. Member CD is made of steel and is a cross-sectional and has a cross-sectional area of 2.5 inches squared. Indicate whether the member is in tension or in compression. I'm gonna really quickly kind of draw out this this thing here. Let's see. Boom. 1, 2, 3, 4. 1, 2, 3, 4. Boom. And then we've got boom, boom, boom. Yeah. This is D. This is C. This is A with a pin support. This is B with a roller support. Got some dimensions here. It's 4 feet. This is 5 bays at 3 feet, which gives us a total of 15 feet from end to end on the horizontal X. Then we also got a vertical load here of 100 kips. All right, so one of the first things that we need in this problem, as we are all kind of aware already anyway, is our moment. We've done this plenty of times before in the past, so some of the moments about B, I want to make that set to equal to 0. And so therefore, we've got our AV equal to 80 kips there. One thing I want to make note for the next portion, which kind of factors into all this as well, which I won't go too much into it because that was in the previous chapter, but we've got our right triangle here. This would be 4, this would be 3, so that means this is a 3, 4, 5 triangle, so our hypotenuse is 5 there. And so therefore, if we take our free body diagram, this is 80. This is 100. And so therefore, the sum of the forces in the vertical is going to be our 80 minus 100. Just keep in mind that we also have our CD value. Oops, not that. CD 4/5. So therefore, CD is 25 kips. And so for our elongation, we have PL/AE. P is 25. L being 5 multiplied by 12 because it's in inches. A being 2.5. And then E being 30,000 for steel. This gives us a value of 0.02 inches for elongation. And the last thing we want to do is just check our stress level just to make sure it is not past our proportional limit. So therefore we can check 25 divided by 2.5, which gives us 10 KSI, and our (34 KSI for the prop limb, so therefore this checks out. Alrighty, I believe that's all the problems that we had here for this homework set. Definitely let me know if you guys have any questions. I will be uploading the transcript of this onto Blackboard. And of course, if you would like to use that as well, you are more than welcome to. Otherwise, we will be jumping over into chapter 11 here shortly, and I'll have the video uploaded as well in the next couple of weeks. Thanks.